Okay, so I kind of changed the topic I want to talk about and just prepared it like last night, but hopefully it's more fitting to this workshop, because it seems that I look back into my previous work and it seems like there is some kind of gap amplification. So I want to kind of tell you, and maybe I want to see if there is some connection to the known techniques in this community. Yeah. Okay, but let me start with a story. The problem that we're gonna consider in this talk is about an oracle that you can query max flow value. Okay, so you have a graph, let's say n vertices, and you want to build a data structure, right? This one, such that you can support max flow query. And let's say you just care about value. So given u and v, then just return what's the max flow value from u to v, which is the same as min cut between u and v. And what we care about in this talk is the space that this data structure needs. And okay, if the graph is directed, then you cannot do much. Because consider, for example, if the graph is directed by partai graph of size n by n, like this graph. Now you see that the max flow value between u and v is going to be more than 0, or actually exactly 1, if and only if there is an edge from u to v. So from here, it means that if you just query the max flow value for all pairs, you can just reconstruct the whole graph G. So it means that there are so many graphs, like a 2 to the n square graph. So one of the graph must require n square space. Okay, so that's simple. Now, how about undirected graph? Well, we know that there is a really nice structure called Goldman-Hood tree, which informally is just a tree. Like given any graph here, there exists another tree that basically encodes all the ST max flow value between all pairs in some very strong sense. It's like a really strong, nice tree, but I will not go into details of this. The point is that the space of this tree is is n, because a tree has n minus 1 edges. Okay, that's good. So there seems to be a dichotomy, but this tree is about edge capacity or edge cut, right? So actually there is something in between directed graph and undirected graph with edge capacity, which is when we care about vertex cut in undirected graph. Okay. So yeah, vertex capacity or vertex cut is just a natural thing to consider, right? Because max flow with vertex capacity correspond to min vertex cut. It's like you have S and T. What is min vertex cut? You ask how many nodes you need to delete to disconnect S and T. So it's kind of as fundamental as the edge cut. So we want to study this. Yeah. Okay. And basically, kind of right after people have seen Goldman-Hood tree, they just actually ask, is there something like Goldman-Hood trees for vertex cuts in undirected graph? Okay, so that's the question, and here is a fun history. So in 1990, Garsfield and Nauer shows that actually there is a Goldman-Hood tree for vertex cut. So that gives you ON space, so that's good. But then it turns out to be wrong. So Benzo shows that, okay, this is not correct. But then he suggests that, okay, there is something that called flow tree for vertex cut. So it's something that's still a bit weaker in some sense, but if you care about max flow value, it's gonna give you all of that. So that gives you ON space like certify what we want to do. So it turns out to be wrong as well. Okay. So Hassan and Levin showed that there is a counterexample for this. And actually there is a graph. They showed that there is a graph such that there actually, like among all ST pairs, there exists a graph where like there are n square distinct max flow vertex cut value. Okay, so that already gives you space of n square lower bound. But in this lower bound, they need that your graph has vertex capacity. And what's important about this work is that it's correct. Yeah. So, but okay, but we can still ask, right? Like, what if you look at the like normal graph when each node has weight 1? So mean vertex cut really just asks about can you just delete how many nodes you need to delete, not about the weights. Okay. Right now, like nothing rules out this. Like, is this possible? Yeah. So we show that it's not. Yeah. So we show that even in this unit vertex capacity case, you still need n square space. Okay. But what seems to be fitting with this workshop is that what the lower bound that we show, it doesn't. It's not an exact lower bound. Even if you allow some gap, like of square root n, in the approximation, like additive square root n approximation, you still need n square space. Okay, so I want to show some idea in this. Okay. And what I want to know is that can we boost this thing further to additive n approximation, or some multiplicative approximation? That's the question. Okay. So here I will now talk about the idea here. Okay. So what I will show instead actually is that I will show this lower bound, n square space lower bound, in unweighted graph, unit capacity, but let's say that it's directed graph. Okay. But importantly, there is like this additive gap is still there. Okay. So this is already non-trivial, and it kind of captures the gap amplification idea. To make it work for undirected vertex cuts, like you just need some more idea about graph, but not about gap amplification. Okay. Right. Okay, so the strategy that we want to do is this. When we try to prove space lower bound, we try to like use some information theoretic technique, right? And the strategy that is too good is just going to be something like this, where you have this oracle. Suppose that this oracle can approximate the max flow value up to root n. Yeah, up to root n additive approximation. Now we're gonna just, let's say I fix some target matrix T of size n by n. What I will try to show is that there exists some graph that depends on T, such that by querying this, or like by querying the oracle on this graph, then I can reconstruct T. So if I can do this, it just implies, like naturally, that some of the graph you need to spend n square space. Like for some of the graph, this oracle needs n square space. Okay. But this is not exactly what we're gonna do. We're gonna do something similar. We're gonna show that, okay, given this target graph, you can construct some graph GT such that from just by querying the oracle on this graph, I can construct some almost a target T tilde, where this T tilde is close to T. Like they differ on only 1% on the entries. Okay, so T tilde is is basically T up to this many entries. And if we have this, we are done too. Like we can still say that one of the on some of the graph, like on some graph, the oracle still need to spend like n squared space. So why is that? Well, error correcting code, right? Because you know that like there are still like 2 to the n square many matrices such that the Hamming distance are just far away from each other. So if you can basically construct, like if you can always recover something close to the matrix that are far away from each other, you can still recover recover the T. Yeah. So that's the goal. Good, right?
You have to make sure that it's space efficient also. Here, like your algorithm in that you recover something that goes to the ground truth, and then you apply some other algorithm to error correcting code. But that part has to be with small of n square space also. That true or not?
I don't think there is anything more than this. Like I just said that I gave like fixed T. I can construct, like given this oracle, I can construct something close to T. There are so many such T. So the oracle must spend large space on some T. Okay. Good. So that's the idea, that's the strategy, and here is the key lemma. Key lemma is about some kind of approximate matrix factorization. That is, given this target matrix T, there's going to be like, I'm going to define, like, let's say that C is some large constant, and A is going to be the matrix of size n by Cn. B is the matrix of size, thing like this, yeah. Given this matrix, there's going to be like this matrix A, where this is of size n, this is Cn, this is Cn, this is n. C is a big constant. Okay? And think of C as the multiplication of A and B. So what we will show is that given any T here, there's going to be, there exists A and B of this size, like it's kind of larger size, okay? Such that basically when you multiply A and B to C, this C kind of capture what T is in this sense. So if an entry of T is 1, then the entry of C, the corresponding entry of C, is going to be big, bigger than like some threshold, Tn plus some gap root n. And if the entry ij of T is small, is 0, then the entry of C here is going to be small too, less than the threshold and within some gap, with some gap here, minus root n. So this is going to be true for basically all entries except like this 1%. Okay. So you see the definition how T and C are similar. Okay. So if we have this, then we are done. Want to claim? Okay. So how? So suppose that I can recall if I can construct A and B like this, right? So we will basically now construct the graph GT. The graph GT, given T, right? And let's say that the axis A and B from this lemma. Okay. Now I construct the graph GT like this. It's going to be 2-layer graph. This is GT, where the first layer is of size n, like 2 layers of edge graph, or 3 layers of vertices. This is of size n, this is of size Cn, this is of size n. And we just build this graph from the 2 matrices A and B in a natural way. If A from I, if entry ik of A is 1, then just put an edge from I to k here. If this entry is 1, from k to j is 1, then put an edge here. Okay. That's just how you build the graph from A and B naturally. Okay. And you can see that, in this graph, the max flow value from I to j is just going to be exactly the number of paths from I to j, which is the same as the entries of C in ij, at ij. Okay. So when you query max flow value between this first and last layer, you basically know what is the value of C on each entry. Okay. So now look at this graph GT. Now I can define my almost target T tilde as follows. Just set T tilde at entry ij to be 1 if the estimate flow value from my oracle says that the flow value is more than 10n. Okay. So why are we done? So if Tij is 1, then this is going to be more than 10n plus root n. And so when I query max flow value from I to j, it's going to be I have some approximation that is less than root n. So my estimate is going to still be more than 10n. Similarly for the case when this is 0. So basically, I'm going to be correct. T tilde is going to be the same as T on every entry such that this is true. But this is true for all entry except a 1%. So it means that the Hamming distance between T tilde and T is just at most 1%. All right. Okay, so with this, we are done. We can, if I can construct this matrix A and B, I can obtain my almost target as I want. All right. Good. So now it's really about this matrix factorization. So that's the goal. You have target T. You want to factorize it into A and B that of larger size such that when you multiply A and B to get matrix C, C and T are basically similar in this sense. Okay. Right. And what we're going to do is we're going to do something that implies this, which is I will define some random process such that I define A and B randomly. And actually for every entry, we get this with 99%. So in expectation, this is going to be wrong on 1%. So that's now our goal. So if t is 1 on this entry, c must be big on this entry with 99%, and vice versa. Okay. Just want to write down some picture. Okay. So again, you're given t, I want to find a and b such that when you look at the multiplication of a and b, it's similar to t. In the graph view, you can think of t as a bipartite graph, right? And what we want to find is find gt that is defined by matrix a and b like before. Okay? And we want that the approximate max flow between this layer, first and last layer, kind of correspond to t. That's the graph view. It's the same thing here. In particular, maybe if you focus on just one node, I, the max flow from I to everyone in J to everyone on the last layer here should correspond to the ith row of T. That's what we want to do. If you look at the node I here, and you look at the value, max flow value to everyone here, you can read off, your goal is to read off the row I of T, the ith row of T, from kind of single source max flow value. Yeah. Okay. So now is the core idea. How do we generate A and B? B is simple, just random. Just put an edge here with probability 1/2. That's it. That's B. So this is B. This is random. The core idea is in A, which is this part. This is A. So here we do this. Maybe let's focus on the first node in A here. Okay, and I tell you how do we construct A. So what I'm gonna tell you is that which node in this layer this guy should connect to. That's I need to tell you. And how do we do it? So we're gonna kind of at the end I will connect to exactly 20 and many neighbor here. I will find 20 and many neighbors. Okay. And how? So I'm gonna find a node K here. Such that the row K of B and the row I of T are correlated. Okay. And if they are correlated, then I set I link from this guy to K. So let me give picture. So basically, I'm gonna connect this to several guys, okay? And then, what is row kth of B? The kth row of B. It means that if you look at this neighbor of this guy, it cannot correspond to some vector, right? That's the kth row of B. Okay. And we want this vector to be similar to the first row of T, if this is the first guy here. Okay. So we want this vector to be similar to row I of T. If they are similar, then I put an edge. Okay. So basically, among all of this neighbor of the first node 1 here, the neighbor pattern from K to J is similar to the first row of T. That's the construction. So I just look through all the case who has a similar pattern to the ith row of t, then connect. And how similar? Well, like this much, like just a bit more than half. And if the threshold is just half, then this happen with half probability. But like I just add this root n, still gonna happen with constant probability. Okay. Okay. So it means what? It means that okay, this happened with constant probability. So I actually expect this many to be discorrelated. Like the number of cases that are discorrelated is like a c times p times n, which is way more than 20n. So I can find this 20n case guy. This is with high probability. Okay. So that's the construction. Is it clear?
So here only you see to be a large constant.
Yeah, set C to be big. Yeah.
But not like super constant. It's a large constant.
Large constant is fine. Just depends on P here. Yeah. Okay. That's the construction. And now let's analyze it. We want to say that if an entry T is big, then T, like that entry of C is big too, with good probability. And to analyze this, let's just think of I as 1. It's going to be the same analysis for every I. Okay? And the picture that you might want to have in mind is like, let's say that, okay, look at the first I is 1. So we kind of focus on the first row of T. And let's say, think in your mind that the first row of T is kind of looks like the first half is 0, and the second half is all 1s. So that is just easier to think about. In the graph view, it means that if this is the first node in T, it just have only neighbor here. Right. And what we want to show is, what we want to show here means that, like, if this is in GT, in the two-layer graph, the max flow value from this guy to the second half here should be big. And the max flow value to the first half here should be small. Right? Okay, let's analyze this. Yeah, focus on the first node here. All right. And let's consider all the cases such that I put like that all the cases that are the neighbor of this node 1, okay, which is this guy, 20n of them. Okay. So among all this case, we know that like this row, the kth row of B is similar to the first row of T. We have this. Row K of B is similar to row 1 of T. So just imagine for easiness that actually they are the same. Then let's analyze what happened. Okay, so if they are really the same, then it means what? It means that for every node here, it has only neighbor to this second half, right? Because I assume that the first row of T, row 1 of T, looks like 0 and 1 here. If this is the case, then it means that like every single guy here looks like just only have neighbor to the second half of J. Make sense? Like the pattern of how this connect from how K connect to J is the same pattern as the first row of T. Okay. So it means then now if I ask like what is the max flow value, like let's say that what's the max flow value of this guy to each of this guy in the second half? Well, it's gonna be 2n because I can go from this guy to anyone here, and anyone here can come to like let's say this node is j. I can go to 1 to 20n many guys, and then to j. So there are like a 20n many paths from 1 to j. What about if j is actually here in the first half? Then there is no way to go to j, right? Because from 1 I can only go to my neighbor, 20n many of them, but none of them connect to j. Okay. So if we have this inequality, we just get this correlation, like this correspondence clearly. That if like t ij is 0, this is going to like max flow value from I to j is 0. Otherwise, it's 20n. But now, okay, we don't have this exactly, but we have that rho k of b is similar to rho I of t. And agreement is basically like 1/2, but with some bias. With bias of plus root n, 1 over root n. And now you just calculate. Like, I will not calculate this, but it's just really intuitive to you, right? That it's basically similar and with some bias. And so in expectation, like if this is 1 in expectation, like the max flow value from 1 to j is going to be this much plus some like times this bias. And if this is 0, sorry. This should be 1, this is 0 here. Yeah.
Because like you're adding, I mean that's fine because you're scared.
Okay. I don't detect the error yet, but if you are good, you're good.
20n times 1 over root n is 20 root n plus 20 over root n. But yeah, so that's what.
All right.
So.
I don't know yet, but okay, good. All right. Anyway, in expectation you have this gap of something like O of root n. Okay. And this is also like you can apply Chernoff bound to this too. So you ask like if this is 1, what is the probability that actually the value of c is less than plus root n instead of I see what you mean. This is root n. This is root n here. Okay. What is the probability that the value of c here is less than this much? We expect 20 root n here, and we ask like what if it deviates from 20 root n to just root n? So the deviation is like 19 root n. Okay. So like that cannot happen with small probability. So with this we get this main lemma and we are done. Okay. So what I want to conclude is okay, now you see how to kind of amplify the gap, but the gap is quite small, it's root n. Okay. And I want to ask if you can amplify the gap even more. Okay. Is there a connection to known techniques in this community? Yeah, thanks. Yeah.
Any questions? So I mean, Let me ask this, might not be correct question to ask, but do you think like, because like that gluten is nearly tight for the like sub-Gaussian variant, so do you think it's like hopeless to do the same approach, or did you try to, you know, maybe massage it with some fancier ways to get like better than gluten and error?
Like the goal of this paper actually is about exact. We didn't care about approximation until like I noticed that it's related to this workshop. So yeah.
Yeah, so where do you use the fact that it's vertex cut and not edge cut?
Right. So like in this graph is directed actually, right? But once you can see that the cut value actually is like something like 10n plus or minus root n. So once the max flow value is around order of n, then there is a way to like extend this lower bound to vertex cut.
But not for edge.
Not, yeah.
Your T is not symmetric, right? It's not a symmetric matrix.
No, it's not. Yeah.
If it was, there are a lot of rules that could be used. So maybe for undirected, for instance, you can look at A and B as points, n points in Cn dimensions, and you're given the distance matrix T. And you want to know if there are actually n points whose distance matrix corresponds to T.
I see.
Parson and I have some paper on this.
I see. Cool. I'll look into it.
Let's thank Thatchaphol again.